So here we're going to do another example. We're given a cubic polynomial. F of x is 3x cubed minus 7x squared minus 43x plus 15. What we're going to do is we're going to use the rational zeros theorem to list the possible rational zeros for the function. Then we will use those zeros to factor this function, this cubic function, down into 3 linear factors, and then we'll state the zeros. All right, so the rational zero theorem, we talked about this in a previous video. I've pulled that in here for us. And what the rational zeros theorem says is that if I have a polynomial, I can create a pool of numbers to draw from and to test with synthetic division. So if I didn't have this pool of numbers, I would just have infinite possible zeros, and I would be picking and choosing and testing them using synthetic division. But with this theorem, I can take the factors of the constant, divide them by the factors of the leading coefficient, separate them out, and this is going to give us a small set of possible zeros. And I say small because it might give us 20 zeros, but 20 zeros is infinitely smaller than just randomly choosing zeros. So I'm going to create a set, and it's going to be plus or minus factors of the constant. My constant is 15, and those factors are 1, 3, 5, and 15, over factors of my leading coefficient, which is 3. So 3 and 1. So this creates a set of numbers for us, right? So for part A, my possible set, I have plus or minus, so 1 over 3, 1 over 1. 1 over 1 is just 1. 3 over 3. 3 over 3 simplifies to 1, which I already have listed, so I don't need to write. 3 over 1 gives me 3. 5 over 3, 5 over 1. And 5 over 1 I have listed, or I can simplify, so I'll just write that as 5. 15 over 3. 15 over 3 simplifies to 5, which I just wrote, and 15 over 1. So I have this set of 6 values here. Of course, we need to use plus or minus. So that plus or minus that we have in front means it is 12 possible zeros. Okay, and that's 12 possible zeros that we're going to test in synthetic division. So, again, you're saying, Ms. Stein, I don't want to test 12 numbers. Well, 12 is infinitely smaller than the other option, which would be infinite zeros. So I'm going to pick a number, and you may not pick the correct number the first time, right? The good news is you have your graphing calculator in front of you, so you can look at the graph on your graphing calculator. We're just trying to understand what's happening so that we can use this if we didn't have a graphing calculator. And when you think about the advent of graphing calculators, the first handheld 4-function calculators, which were actually pretty large, those didn't come about till the late 60s. And students didn't have graphing calculators in their classrooms until somewhere in the mid-90s. Okay, so people have been doing math for about 2,500 years, yet we've only had graphing calculators in our hands for the last 30 or 40, right? So people had to figure out ways to do math without a calculator. There's a little minor history lesson for you. So back to our problem here. We need to factor this, and we're going to choose a possible zero. So we could choose any number on that list. We just want to choose a rather small number to deal with. So I might lean towards choosing 1. And if I choose to test 1. I'm going to plug x equals 1 in and test that in 3, -7, -43, and 15. Okay, and those numbers are coming from my original polynomial. So when I do this, I'm going to pull down that first number. We have 3 multiply 3, -4, -4, -47. We do not get 0, right? So if I had to test 12 numbers like that, it's not going to take me a load of time. And you may choose incorrectly the first time and have to do it again. So I'm going to pick a different value. I'm going to repeat this process. And I'm going to choose, say, x equals 5. And x equals +5 is a number in my list. Remember, we could have the plus or the minus of all those numbers in my list. Choosing x equals 5, bring down the 3. I got 15, +8. 5 times 8 is 40. -3, 5 times -3 is -15. So we get the desired remainder, 0. And getting that 0 as a remainder, what that allows me to do is to take my function and we started with 3x cubed minus 7x minus 7x squared minus 43x plus 15. And now that I got that 0, I can factor this. So my first factor comes from x equals 5. That gives me a factor using my factor theorem of x minus 5. And then my quotient is going to be 3x squared plus 8x minus 3. So I've factored this polynomial function. We started with a cubic function, and now we have a linear and a quadratic factor. So we're working towards part B, and part B of our problem says we need linear factors. So f of x equals x minus 5, and this quadratic factor, I know how to factor that. That's going to become, let's see, I've got 3x and x. If I put a +3 here and a -1 there, I get 3 and 9. So now I've factored this into linear factors. So my last part says, well, if you wanted to state the zeros would come from saying, I don't like the way that looks, x equals +5, which we got from our synthetic division, and then these two other factors, we would get 1/3 and -3. So these are the 3 zeros of my cubic polynomial.